Welcome back. In previous video, we looked at some of the intuition behind pseudo inverse and how it works. In this video, we'll look at examples of an orthogonal input first and then a non-orthogonal input and see how the signals overlap, how the pseudo inverse sort of helps us extract the patterns if from that, and if there is any interference with between patterns in case of non-orthogonal inputs, do we see that in the target output that we get. So the first case we will look at orthogonal inputs, and in this case, let's say our input, we have two input vectors, p1, and p1 is 1 0 0, and then we have a second input vector, and that one is 0 1 0. And if we try to get the dot product of these two, we should get a 0. So let's try and do the dot product 1 0 0 and dot that with 0 1 0. And as you can see, 1 times 0 is 0 plus 0 times 1 plus 0 times 0, and so we do get output of 0. So these two are orthogonal to each other. Now what we can do is create an input matrix P using these two input vectors. So the very first input matrix is 1 0 0, and the second input matrix is 0 1 0. Sorry, input vector is 0, so that this is the p1, this is the p2 that we have. And in the derivation in the last video, we said that this goes all the way up to pq, and we denoted each of these as the lowercase q. Likewise, we would have we need a target, and so for target, let's say we have the target t1 that corresponds to the input p1, which is simply 1 0, and another target for which corresponds to the input p2 is t2, and let's say that target is 0 1. So if we try and create a matrix T using these target vectors, what we get is 1 0 0 1. And now we can begin. So with these two matrices that we have, we can now begin to work on the pseudo inverse topic. So what we can do first is look at the overlap. So let's say we look at the overlap by uh, dotting these two. So we say P transpose P, P transpose dotted with P, and so with the P transpose, we would get right here is 1 0 0, and the second one is 0 1 0. So that's the P transpose. We have the P, which would be simply 1 0 0 0 1 0. And if we try and get the dot product of these two, we get 1 times, so 1 times 1 plus 0 times 0 is 0, plus this 0 times this 0 is again 0, and then 1 times 0 on this side is 0, this 0 times 1 is 0, so 0 plus 0 plus again 0 times 0 is 0, and in the second row we have 0 times 1 is 0, then 1 times 0 is again 0, and 0 times 0 is 0, and on the second we have 0 times 0 is 0, plus 1 times 1 is 1, plus 0 times 0 is 0, and so what we get is the output is 1 0 1 0 1. So that's the value we have for P transpose P, and that is an identity matrix. A point to note here is that these off diagonal elements in this particular matrix are 0, and that tells us that there is no overlap between the signals P1 and P2, and that is important because if we now try to calculate the pseudo inverse, if we say P plus is equal to P transpose P inverse of this, P transpose, then the inverse of the identity matrix is the same. So that is the identity matrix, and inverse would be the same. So if I do so let's say that this is 1 0 0 1, and if you take the inverse of this, it's going to stay the same. So what we can do here is we plug in the values, and so this is going to be the I2, and we multiply or dot that with the p transpose. So we have 1 0 0 1, and we dot that with the p transpose, which is 1 0 0 0 1 0. And if we perform this dot product, what we get is the following. Is 1 times 1 is 1, 0 times 0 is 0, so we get 1, and 1 times 0 is 0, 1 times 1 is uh, so 1 times 0 is 0, 0 times 1 is 0 again, so this is 0. And if you run through this, you get 1 0 0 0 1 0. So in the end, the p plus matrix that we get is again has these elements in the upper triangle which are all zeros. Now what we can do is try and get the weight matrix. So we use that, and we use this particular matrix. So let's write that down again here, 0 1 0. Now if we try and calculate the weight matrix for the Hebb, which is equal to T, uh, T is T dotted with P transpose. This is what we have for T, and then we dot that with the P transpose, which is 0 1 0. And if you do this dot product, you will get 1 0 0 0 1 0. And so as you can see here, the weight W P inverse, if we try to calculate the P inverse, that is the pseudo inverse, then that is going to be equal to P plus, which we have above. And so again, I would use the same target, and we dot that with the P transpose, which is the same that we have just calculated above. And if you look at the output of this, this is equal to uh, it'll be the same matrix that we just calculated above, and so we can say that this is equal to the weight matrix we get from Hebb. So that's the key point that we are able to relate these two. Now if we try and recall an input, let's say we input P1. If we input P1, which is 1 0 0 to our weight matrix, then what do we get? Do we get the target? So let's say A is the output, and for Hebb we say that W Hebb is equal, and we dot W with P1, and so the W that we have is 1 0 0 0 1 0. We dot that with P, which is 1 0 0, and what we get in the output is, and this would be 1, then we have so 1, and then the second one would be 0. So this is equal to T1, and that's a perfect recall, so perfect match with the target, because we up above we see that the T1 is 1 0. Likewise we can also check for P2, which is 0 1 0, and if we calculate the output, that would be equal to 1 0 0 0 1 0, and here we have 0 1 0. And so again the output that we get is the exact match that we had above, which is 42. So the take home message here is that because the inputs P1 and P2 are orthogonal, what made that possible was the dot product of P transpose P. It was diagonal, and in diagonal we saw that the off diagonal elements were 0, and that allowed us to get a perfect recall. Now let's look at non-orthogonal case. So in the non-orthogonal case, let's see the inputs. So I'm going to scroll down here. So for non-orthogonal inputs, let's say we have the two inputs P1 is equal to 1 0 0, and the corresponding T1 with this is 1 0, and P2 is 1 1 0, and the corresponding input target output for that is 0 1. So if we try and create a input matrix, we would have 1 0 0 1 1 0, and the target matrix would be 1 0 0 1, same as before. And just to check if these are orthogonal or not, we can do the dot product here. And so what we have is 1 0 0 dotted with 1 1 0, and so what we get is 1 times 1 plus 0 times 1 plus 0 times 0, and so we get a value of 1 which is not equal to 0, and therefore we can say that these two are not orthogonal to each other, and that's exactly what we are looking for. So what we can notice right here in the input itself is that there is an overlap, and we can see that uh, both have the first component, which is 1. So this has this 1, and this also has the first component 1. So that's where the overlap is in this case. We can now proceed with the calculation. So the P transpose, we can calculate the P transpose P. So P transpose P is equal to 1 0 0 1 1 0, and we dot that with 1 0 0 1 1 0, and that gets us the following: 1 times 1 times 1 is 1, plus 0 plus 0, and then we have 1 times 1 is 1, plus this is going to be again 0. So this is 1 times 1 is 1, right, and then 0, and then again we have another 0. Here we have 1 times 1 is 1, plus 1 times 0 is 0, 0 times 0 is 0, and finally we have 1 times 1 is 1, plus 1 times 1 is another 1, plus 0 is this is 0. So in the output we get 1 1 1 2, and as you can see, it's we now have off diagonal elements uh, here and here which are non-zero, and that's where we see that there is an overlap between the signals. So off diagonal values equal to 1 or equal to 1, or they are non-zero. Now let's keep going and try and invert the P transpose P. So for just a note, when we do an inverse, let's say if we have A, B, B, C, this matrix we're trying to get inverse of, what we would do is we calculate a determinant that would be A times C minus B times B, which is B square, and then we swap the AC to CA, and then we flip the signs on the off diagonal elements. And so in this case, when we try and calculate the P transpose P inverse, what we would get is the following. the determinant in this case would be, so this is, let me just write this clearly, just remove those arrows to avoid any confusion. We have 1, so we what we get is 1 times 2 minus 1 times 1, and here we swap these two, flip the signs on those, and so that gets us a determinant of 1 divided by 2 minus 1 is 1, and here we have 2 minus 1 minus 1 1, and so our inverse is this. We can now calculate the p plus. So p plus is equal to, we already have the inverse, we simply dot that with p transpose, and so let's do that. Minus 1 minus 1 1, then we dot that with the p transpose, which is going to be 1 0 0, then we have 1 1 0. So what we get here is the following: 2 times 1 is 2, and minus 1 times 1 is minus 1, so this would be 2 minus 1, so we get 1. Then 2 times 0 is 0, minus 1 times 1 is minus 1, so 0 minus 1 we get a minus 1, and then the other one is simply 0. And similarly, down here we would get 0 1 0. So the p plus that we have, this matrix that we have is 1 minus 1 0 0 1 0. Now what we can do is check if the p transpose p, p plus p gets us an identity, uh, and we can do that by simply doing this dot product. If we say 1 minus 1 0 0 1 0, and the p is 1 0 0 1 1 0, and if we solve this, we get 1 times 1 is 1, plus 0 plus 0, and then 1 times 1 is 1, then we have minus 1, then we have a 0, and here we have 0. All of these will be 0, so 0 plus 0 plus 0, and down here we would have 0 plus 1 plus 0. So we do get a identity matrix out here. So the this is required for independent columns, and so that is great. Now what we'll do is calculate the Heb, the weights. So the first thing we'll do is calculate using the target T and the P transpose. So the target is 1 0 0 1, and the P transpose is 1 0 0 1 1 0, and that gets us 1 times 1 is 1, 0 times 1, so this is 1, and then this is 0, this again is 0, and then down here we have 0 plus 1, so this is 1, again 0 plus 1, this is 1, and then the next one is just 0. And see, we now have calculated the weight matrix for the Heb using the target and input. Now we will calculate the pseudo inverse weight matrix W, P, I, and V, and this is T target dotted with the P plus, and so what we get is 1 0 0 1, and our the P plus matrix is 1 minus 1 0 0 1 0, and that gets us 1 minus 1 0 0 1 0. And now what we will do, try to recall with each of these. So we'll try and recall with the W Heb and then the P inverse that we used here, and each of these cases we'll see what the output looks like. So let's start with the Hebbian recall. So Hebbian recall, where we'll use the W Heb. So the first one is for P1. So A Heb using the P1 is going to be equal to W Heb matrix that we calculated above dotted with P1, and so we have 1 0 0 1 1 0 dotted that dot that with 1 0 0, and if we calculate this 1 times 1 is 1, rest are 0, so we get a 1, and again we get a 1 here. So this is not equal to the T1 that we have, which equals 1 0, right? So that's the first thing we notice. Second thing is when we try and calculate the same thing using P2. So let's try that. P2, we have W Heb dotted with P2. Again, we have the same weight matrix 1 1 0, and we dot that with the P2, and so here what we get is 1 times 1 is 1, rest are 0, again 1 times 1 is 1, that happens 2 times, so we have 1 plus 1 2, and again this is not equal to T2, which is equal to 0 1. So as you can see in both these cases, uh, the recall is not perfect, so there is interference from P2 in this case and P1 in this case. What we can now do is use the pseudo inverse and see what happens. So pseudo inverse recall. Here we calculate A P inverse used for P1, and for this we use the matrix W P I N V and dot that with P1. So our WPI and V is right above, which is 1 minus 1 0 0 1 0, and we dot that with P, which is 1 0 0, and so that gets us 1 times 1 is 1, and this is 0, and the next one is 0. So the first value is 1. In the second case we have 0 0 0, so this is 0, and as you can see, that is a perfect match with T1 that equals 1 0. Awesome. And the second, we can try and calculate the value for the input P2. So this again would be the same. We dot that P inverse weight matrix for the pseudo inverse with P2, and this is going to be the same matrix right here, and the same and we change the output the input to P2, and when we do the dot product multiply these, 1 times 1 is 1, and 1 minus 1 times 1 is minus 1, that cancels out, we get a 0, again here 0 1 and 0, so this becomes 1, and again you can see that using the pseudo inverse matrix, when we calculate the output target, we get a perfect recall, a perfect match with the T1 and T2. So the takeaway message in these two examples is that when input patterns are orthogonal, when the input patterns are orthogonal, then the Heb's outer product rule works already. So what I mean by outer product is when we do the T P TP transpose. Uh, that's good. When the inputs overlap, the Hep produces interference, which we saw right here. Where is it? Where Hep? Yep. So right here we saw this interference, and that so we don't get a perfect recall. But when we use the pseudo inverse, uh, which we did here, then that mathematically cancels that overlap and gives us an unique least squares matrix, which is equal to this TP plus, and that exactly maps the stored inputs with the targets as we see here. So that was it for these videos where we looked at pseudo inverse, the concepts, and also an example of how it works. If you have any questions, comments, or suggestions, please do let me know in the comment section below. Thank you, and I hope to see you all in the next video. Bye for now.